10 and Chapter 11. Chapter 10 has to do with vision, and Chapter 11 has to do with your muscles. So let's go ahead and get started. Maybe, there we go. The whole area that you can see without moving your head or eyes is known as the visual field. While the visual field may be wide, an individual's visual acuity tends to be only in the middle of the field of vision, and that's known as your fovea. That's where all your cones are, in the fovea. Your visual field is about 180 degrees. Your peripheral vision tends to be fairly extensive. Not everybody has a good peripheral vision. I have a brother that has what they refer to as tunnel vision because his eyeballs are set deeper into his skull, so he sees. He doesn't have 180 degrees of peripheral vision, but he has better night vision, as curious as that is. And I have really good peripheral vision, so I can see better during the daytime. Anyway, this is because there's a concentration of cones in the middle of the visual field, an area known as the fovea. And this is what acute vision looks like, and that's what poor vision looks like. Even with the concentration of visual receptors in the center of the visual field, there is a spot where the optic nerve feeds out of the eye and blood vessels feed into the eye. This is known as the optic disc, and this area maintains a blind spot in an individual's visual field. And you can find your blind spot. It's just a little bit off center. And if you move your finger across your visual field, at one point it just about goes away, and that's just a little bit off center. Normally the brain automatically fills in the blind spot, but unless you have enough information to fill in that blind spot, it doesn't. And there are ways that you can see that. It's really kind of fascinating. Vision comes to the humans in the forms of wavelengths of light, or photons. The human visual ability lies between 400 and 700 nanometers. That is ultraviolet to infrared. Other animals have ranges of vision that encompass wider spectrums of light. Bees, for example, can detect beyond ultraviolet light, and that's how they can follow the vapor trail or the heat signature of other bees. So when a bee finds a flower, then he will tell the other bees how much nectar there is, and then a group of bees will go out and, following his heat signature, they will find the flower. They will fly to the flower and harvest all the nectar. A photon of light comes into our eyes with select properties that we will perceive as color. The hue is the wavelength of the light. Wavelengths in the 400 to 500 range are very dark purples to blue. Wavelengths in the 500 to 600 range are greens to orange with yellow in the middle. Wavelengths in the 600 to 700 range are bright reds darkening to black. Since most color is detected as patterns of light of different wavelengths, brightness refers to the amount of white light from the object. Saturation has to do with the amount of light of a select wavelength. If all photons reflecting from an object were at 510 nanometers, the object would be highly saturated as green. And of course, today is St. Patrick's Day, so green is a good color to have on. The eye acts much like a camera. The eye has a transparent sac called the lens, which widens and narrows to focus light on the retina. Also leading to proper focusing is the cornea, or the curved outer cover of the eye, that changes the light beam as it enters the eye. The shape of the lens is controlled by a set of muscles around the lens called the ciliary muscles. When the lens is made to widen or shorten to allow for focusing, it is known as accommodation. And of course, if the ciliary muscles don't move, then there is no accommodation. At birth, about 15% of males and 18% of females have severe enough eye problems to require correction. By age 20, until presbyopia, and presbyopia is an interesting word. It means old eyes. Presby meaning old or elder eyes. Usually hits sometime in your 40s, sometimes into your 50s, but that's presbyopia. About 48% of females and 32% of males require correction. So, people, if you lined up all the people that were 60 years old, about half of the women would be wearing glasses, and about a third of the men would be wearing glasses. Nearsightedness or myopia is where the eyeball is too long and the nearest, clearest focus occurs before the light hits the retina, and that's nearsightedness. Farsightedness or hyperopia is where the eyeball is too short and the best focus is a point that's past the retina. And astigmatism is a misshapen cornea, or it's elongated. That causes the light to pass incorrectly into the eye and cause the individual to be nearsighted. And this is what an astigmatism looks like. This is a normal cornea, and this is an astigmatic cornea. As you can see, the cornea is elongated, and that's all it is. And it causes nearsightedness. The iris is a muscular covering under the cornea that gives the eye its color. Non-brown eyes were a mutation that appeared about sometime between 6,000 and 10,000 years ago. So 11,000 years ago, everybody had brown eyes. And at that point, something happened. A mutation occurred, and people started having blue eyes and gray eyes and different colors of blue, green eyes. The pupil is an opening in the iris that allows light to enter the eye. The movement of the eyeball itself is controlled by extraocular muscles, and that's what moves the eye from side to side and up and down. The photoreceptor cells of most animals are part of the retina on the back of the inside of the eyeball. The retina is a very thin, but still contains 5 distinct layers. The first layer is the optic nerve fiber layer that is working from the inside out. The second layer are the ganglion cells. The third layer are the bipolar cells. The fourth layer is the actual photoreceptor cells themselves, the rods and the cones. And the fifth layer is made up of pigmented epithelium. So the back of the wall of the eyeball is this pigmented epithelium. And if you shine a light into an animal's eyes or a human's eyes, and you get a reflection off of the eyes, that is the epithelium, the pigmented epithelium, shining the light back toward you. And if you look at most animals, they have fairly good night vision, so the reflection that you get back is fairly bright. Humans are red; their eyes reflect red, and thus we don't have very good night vision. The rods and the cones detect light that reflects off the pigmented epithelium. The rods and cones release neurotransmitters that synapse with the bipolar cells. The bipolar cells synapse with the ganglion cells that form the optic nerve. While most of the communication in the retina runs from outer layer to inner layer in a vertical pattern, amacrine and horizontal cells communicate with cells in the horizontal pattern. Horizontal cells connect receptor cells. Amacrine cells connect the bipolar and ganglion cells. The rods and the cones represent different functional systems. The scotopic system consists of all the rods in each eye, 100 million cells. The scotopic system is very sensitive to weak light, but cannot detect color. Light is captured in the scotopic system by the photopigment rhodopsin. The scotopic system is located primarily outside the fovea. The photopic system consists of all the cones in the eye, about 4 million. This system detects color and requires relatively strong stimulation and therefore is primarily a day vision system. The photopic system is located primarily in the fovea but is present in other areas of the retina but in a lower concentration. There are three forms of photopigments called opsins that detect the three color groupings. The photopigment for the scotopic system is rhodopsin. The photopigment for the photopic system is one of three configurations of opsins. All the photopigments in the eye are made up of two parts, retinol and opsin. Retinol is short for vitamin A aldehyde or retinaldehyde, shortened to retinol. Light activates the rhodopsin molecule to rapidly lose its retinol, leaving an enzymatic receptor site on the opsin molecule. The enzymatic opsin molecule combines rapidly with G protein transducin. Transducin, in turn, acts on phosphodiesterase to convert cyclic guanosine monophosphate, or cyclic GMP, to 5-GMP. Cyclic GMP inhibits sodium channel, the sodium channels closing, and with the conversion, the sodium channels close. The loss of sodium ions depolarizes the neurons. Since we are dealing with millions of receptor cells at the same time, weak light will only hyperpolarize some of the receptors, and bright light will hyperpolarize most of the receptors. Thus, the response will always be graduated as to the amount of light that is detected. This form of response leads to sensitivity. It allows for adaptation. It allows the individual to integrate the stimulus over time. There are two types of bipolar cells that transmit information: off-center bipolar cells and on-center bipolar cells. On-center bipolar cells are activated when light is turned on. Off-center bipolar cells are activated when light is turned off, so that the eye still has visual capabilities. It detects light coming in from the periphery of the visual field. Photoreceptor cells release the neurotransmitter glutamate. Glutamate is decreased in off-center bipolar cells when light is weak or turned off. Glutamate is decreased in on-center bipolar cells when light is turned on in the middle of the visual field. Each cone in the fovea is connected to four types of bipolar cells: one on-center midget bipolar cell, one off-center midget bipolar cell, several on-center diffuse bipolar cells, and several off-center diffuse bipolar cells. Each midget bipolar cell connects to just one cone in the fovea. Each diffuse bipolar cell connects to several cones. When light is turned on-center bipolar cells depolarize on-center ganglion cells. When light is turned off-center bipolar cells depolarize off-center ganglion cells. Stimulus only affects the part of the retina that is in the visual field. The retina will create a mosaic of stimulation that the brain puts together as a picture. There are various ways that the eye adjusts to different light intensities. The pupil of the eye will shrink with bright light and widen with dim light. Rods and cones have different thresholds. This is range fractionation. Photoreceptors will adjust their range of reaction depending on the intensity of the light. This will give the individual visual acuity despite the quality of the illumination. Calcium is a major player in photoreceptor light adaptation. When an individual changes from one extreme light to another, it takes time to adapt to the new intensity of light. This is because the retinol and opsin break down at a higher rate in bright light and must regenerate to be available in the dark. Adaptation is much quicker when adjusting from dark to light because the retinol and opsin level is not depleted. Color acuity is more accurate in the center of the visual field because the fovea is almost exclusively cones. Moving out from the fovea, the number of cones decreases and the number of rods increases. Light sensitivity is most acute about 20 degrees off center, where the concentration of rods is greatest. And of course, that's the way you're trained when you're in the military. They train you to not look directly at a light that you think you'd see, but to look at about 20 degrees off. And then you can see the light much, much better. Which may be one of the reasons why we see ghosts and that kind of thing. You can detect it off center, but if you look directly at it, it disappears. About half the primary visual cortex, V1, is devoted to the fovea. This is one of the reasons that humans are able to concentrate their special field on tasks close at hand, such as reading and surgery. A scotoma is a gap in a perceptual field, usually due to an injury of the visual mapping area of the brain. People with scotoma will often compensate for their problem by allowing the part of the brain not affected to dominate the affected area. And this is known as blind sight, where your brain fills in the picture that it sees. Okay, so if you look at this red cross right in the middle of the field, it looks like all of these things are moving. All of these white and black squares are moving. But one of the odd things is, if you look at this long enough, your brain will fill in this gray spot right here. It gets smaller and smaller and smaller. And that's because your brain is actually filling it in with what it sees. So when you look at it initially, it's fairly large, but the more you concentrate on the red cross in the middle of the field, the more that gray spot will disappear. And if you look at this long enough, then the gray spot will disappear completely. And that's what happens in scotoma. Each eye is divided into two parts: the nerves of the temporal half of the visual field, the one on the outside, and nerves of the nasal half of the visual field. As the optic nerve leaves each eye, the nerves come together in an area known as the optic chiasm. At the optic chiasm, the nasal optic nerves cross to the opposite hemisphere, and the temporal optic nerves stay on the same side. After the optic chiasm, the nerve pathways are known as the optic tract. Most axons of the optic tract terminate in the lateral geniculate nucleus, or the LGN, of the thalamus. From the LGN, the axons radiate into the primary visual cortex, the V1, of the occipital lobe. The primary visual cortex is sometimes called the striate cortex because of the striations that run through the area. Visual areas of the brain not in the striate cortex are known as extrastriate cortex. Some axons of the optic tract send their axons to the superior colliculus, where the superior colliculus helps the eyes track rapid movements. And we can do this, but sometimes, and cats can do it when it goes across their field. But if it comes from straight down, if something enters their field from above and hits the ground below, a lot of times they won't see that because their eyes are focusing on things moving from side to side. But as humans, we can track rapid movements very readily because our eyes are round. Their visual field is mostly from on the same level as they are, and it moves from side to side. The LGN is arranged in 6 layers. The outer 4 are the parvocellular layers, and the inner 2 are the magnocellular layers. P cells from the parvocellular layer have small receptive fields, while the M cells from the magnocellular layer have a large receptive field. Magnocellular cells are sensitive to low contrast and rapid change. About 10% of the retinal ganglion cells are M cells. 80% of the retinal ganglion cells are P cells. P cells require high contrast to be stimulated. P cells are relatively insensitive to rapid temporal change, such as flicker. P cells are sensitive to different wavelengths of light, and they therefore detect color. P cells have sustained responses. P cells have high acuity. And this is one of the reasons if you look at a computer screen, you don't see any flickering. But if you look at a computer screen in a movie or on television, a lot of times the screen will look like it's flickering. And that's because they're taking individual pictures of it. And the individual picture will see the flickering, but your eye will fill all that in, and it doesn't see flickering at all. The primary visual cortex, the V1, is the first and most abundant area in the human brain. From the V1, the stimulus is farmed out to other areas of the brain, depending on what part of the eye the stimulus comes from. Areas are designated from V1 to V5. Researchers have discovered that there are 3 different kinds of cones. Cones that are sensitive to short wavelengths only, cones that are sensitive to long wavelengths only, and cones that are sensitive to the middle wavelengths. Of the middle wavelength cones, some are more sensitive to the higher ranges of middle. Some middle range cones are more sensitive to the lower range of middle. There are twice as many long wavelength cones, reds, as middle wavelength cones, greens and yellows. Short wavelength cones are the fewest, the purple and blue. So this is maybe one of the reasons why a lot of people, their favorite color is red, because there are more cones that actually see red than there are that see green or blue. Any other color but red. Myopia is a condition where the eyeball is elongated, causing the image to focus on in front of the retina, causing a blurred image. There is some evidence that nearsightedness is caused when children look at images too close to their faces. This can be prevented by only allowing reading in adequate light, avoiding small type, reading without glasses anytime that you can do so, to condition the eye to see its natural sights. This is what myopia looks like. And oh, come on, there it is. It corrected itself. Okay, now it's going to get fuzzier and fuzzier and fuzzier. Glaucoma is a group of eye conditions that damage the optic nerve, the health of which is vital for good vision. This damage is often caused by an abnormally high pressure on your eye. Glaucoma is one of the leading causes of blindness for people over the age of 60. And I have a brother with glaucoma, and of course he thinks that we have the same genes, and he warned me that I needed to get my eyes checked to make sure that I don't have glaucoma. I don't. And I'm 75. He was diagnosed with glaucoma in his 40s. So he's had to put eye drops in his eyes every day for the last 35 years or so. And that is that. Okay, so let's move on to motor control and plasticity. Short chapter. Muscles cover the skeletal system and provide movement. They also provide protection for the organs that lie underneath. How muscles attach to the bones is an indication of the type of movement that they perform. Muscles only provide force when they contract, when they tighten up or get smaller. So when you have your arm stuck straight out, your bicep is flaccid. It's not tightened up. And in order to tighten that muscle up, you need to shorten that muscle, and that it means to bend your elbow. Some muscles maintain body posture. Some muscles produce movement around a joint. Any movement that occurs in the body is performed by muscle. Muscles are connected to bone by tendons. Around a joint, there are two sets of muscle groups. When one group contracts, the other extends. These muscles are antagonists, and a good example would be the bicep and the tricep. The tricep's on the back of your arm, the bicep is in the front of your arm, and so when you bend your elbow, it shortens the bicep and it makes it larger. And when you stick your arm out straight, it tightens up your tricep and it relaxes your bicep. They're antagonists, and that's what it's showing you. Muscle groups that act together to perform the same act are known as synergists. Muscles are made up of thousands of fibers. These muscle fibers are made up of two kinds of filaments. Thick and thin filaments arranged in a regular pattern. Thick filaments are made up of myosin, and thin filaments are made up of actin. There are two basic types of muscles in the human body. Smooth muscles contract in an automatic fashion without human control, regulating by the autonomic nervous system. Heart muscle and muscles in the digestive tract are examples of smooth muscles. The other type of muscles are striated muscles, primarily supporting the skeletal system, and you can see the difference between the two. This is a striated muscle, and this is a smooth muscle. Since different muscles perform different tasks, each requires different speeds, precision, strength, and endurance. Striated muscles fibers come in two forms, in fast muscle fibers and slow muscle fibers. Eye movement must be quick to follow the movement of speeding objects, but only for short periods of time. Extraocular muscles are fast muscle fibers. Fast muscle fibers react promptly and strongly. They fatigue rapidly. They are used when muscle tension must change frequently. Slow muscle fibers have greater resistance to fatigue, are used mainly to maintain posture, and that would be your standing muscles, the muscles you use when you stand up. Muscles react to stimulus coming in from motor neurons. The axon will split into many branches and activate many muscle fibers. As the axon is activated, it releases the neurotransmitter acetylcholine. Acetylcholine makes the muscle react by opening sodium and calcium channels in the muscle fibers. The iconic change allows the muscles to contract. The point where the muscle fiber and the nerve structure communicates is the neuromuscular junction. Neuromuscular junctions are large and very effective. And there's a neuromuscular junction. Each neuromuscular junction releases enough acetylcholine to not only cause one reaction, but several at the same time. One cause of muscle fatigue is due to diminished effectiveness of neuromuscular junctions. Muscles develop coordination when axon terminals migrate to specific target muscles, and acetylcholine receptors migrate to the clustered axon tips, allowing for more efficient muscle reaction. Muscles react because spinal or cranial nerves send messages to the muscles through efferent neurons. Motor cells of the spinal cord are larger and faster than other motor neurons. Generally, small motor neurons activate slow muscles and are more easily excited. Large motor neurons tend to activate large muscles, which require more stimulation for activation. And this, I hope, it works. There we go. Wait a minute.
The skeletal muscle of animals, including humans, are striated. They exist in bundles of thousands of muscle fibers. A single muscle fiber is actually a muscle cell. As you can see, muscle cells are very elongated and contain several nuclei. Packed inside the muscle cells are contractile myofibrils. Myofibrils show the striated pattern as repeating subunits called sarcomeres. When a motor neuron stimulates a muscle fiber, overlapping filaments in the sarcomere slide along one another, and the sarcomeres shorten. The repeated pattern of the sarcomere results from the arrangement of the two major proteins within the myofibril: myosin and actin. The myosin heads are the actual mechanism for muscle contraction. Now let's examine the process in detail. First of all, when a motor neuron stimulates a muscle fiber, calcium ions are released from the sarcoplasmic reticulum. The ions force the tropomyosin to displace and expose myosin binding sites on the actin. An ATP molecule is then hydrolyzed, and the myosin head forms a cross bridge. When the ADP is replaced by a new molecule of ATP, the myosin head detaches from actin and goes back to its original state. And that's pretty much the whole process. And one more thing. Each myosin head attaches to and releases from actin independently, not in unison. Otherwise, the myosin heads would all release at once, and the whole muscle would go to a relaxed state. And that wouldn't be good.
Okay, that's how it works. The body must maintain control over the position of its parts. This knowledge of the position and state of its muscles and limbs is called proprioception. This knowledge is maintained by select receptors that report muscle and joint positioning. Muscle spindles lie parallel to muscle fibers. Golgi tendon organs report on the position of the joints and are situated with one end attached to the tendon and one end attached to the muscle. Muscle spindles are located in many areas of our skeletal muscular fiber. Muscle spindles are actually spindle-shaped. It consists of an efferent element and an afferent element and an efferent element. Their primary function is to maintain your posture and to tell you when you have been in a position too long, and then you move. When a muscle fiber is activated, the muscle spindle reports rate of change. Rate of change refers to the change the fiber has gone through to be able to function. The muscle spindle also reports force, the force required to maintain contraction. And of course, if you lift weights, you feel this every time you lift a weight. The rate of change and the amount of force that you need. And of course, as your muscles get tired, which is why you're lifting the weights, it tells you how many more reps you can do, how many more times you can lift the weight. Muscle spindles have two types of receptor endings. Primary sensory endings, wrapped around the middle of the fiber, are activated during the initial phase of contraction and then adapt to a lower discharge rate. Secondary sensory endings, found near the smaller ends of the fibers, are not activated at first, but only after prolonged use, and that will tell you when you're tired. Your secondary sensory endings. Muscle spindles are informed of impending action through two special motor neurons. Gamma motor neurons, or gamma afferents, inform of change of position from the initial movement. Comprises about 30% of the efferent fibers. Alpha motor neurons perform initial movement, 70% of the efferent fibers. While individual muscle movement is monitored by the muscle spindle, muscle contraction is monitored by the Golgi tendon organ. Golgi tendon organs are able to monitor muscle and joint movement because joint movement is controlled by tendons connected to the muscles. And it tells you if you're lifting too much. And there's where the Golgi tendon organs are. Golgi tendon organs are somewhat insensitive to passive muscle stretch because they are connected to the elastic component of the tendon and is only activated under heavy loads. Golgi tendon organs detect overloads that threaten to tear muscles and tendons. Activating the Golgi tendon organs inhibits the motor neurons simply supplying the muscles that pull on the tendon, and thus by relaxing the tension prevents mechanical damage. And of course, it would tell you to stop lifting the weight is what it would tell you to do. People that max out a lot, or who max out frequently, they will strain these Golgi tendon organs. And of course, sometimes they will pull muscles. There's nothing uglier than somebody pulling a muscle while they're lifting weights rather than while doing running or whatever. Here, let's do this one.
Muscle building. The key to building muscle is protein synthesis and cellular repair. Skeletal muscle is made up of long fibrous chains containing proteins. Bundles of thousands of fibers make up the muscle itself. When an athlete engages in a heavy workout, this structure is damaged, causing micro tears in the muscle fibers. The body naturally repairs this damage by mending the torn fibers. The result is a muscle that's larger and stronger than before. And with each additional workout, the athlete adds bulk, strength, and speed.
That's the way it works.
How to stay alive in a catastrophic car accident like this, even after falling into water reservoir.
Oh my
A fatal
Muscles. We have over 600 of them. They make up between 1/3 and 1/2 of our body weight. And along with connective tissue, they bind us together, hold us up, and help us move. And whether or not bodybuilding is your hobby, muscles need your constant attention because the way you treat them on a daily basis determines whether they will wither or grow. Say you're standing in front of a door, ready to pull it open. Your brain and muscles are perfectly poised to help you achieve this goal. First, your brain sends a signal to motor neurons inside your arm. When they receive this message, they fire, causing muscles to contract and relax, which pull on the bones in your arm and generate the needed movement. The bigger the challenge becomes, the bigger the brain's signal grows, and the more motor units it rallies to help you achieve your task. But what if the door is made of solid iron? At this point, your arm muscles alone won't be able to generate enough tension to pull it open, so your brain appeals to other muscles for help. You plant your feet, tighten your belly, and tense your back, generating enough force to yank it open. Your nervous system has just leveraged the resources you already have, other muscles, to meet the demand. While all this is happening, your muscle fibers undergo another kind of cellular change. As you expose them to stress, they experience microscopic damage, which in this context is a good thing. In response, the injured cells release inflammatory molecules called cytokines that activate the immune system to repair the injury. This is when the muscle building magic happens. The greater the damage to the muscle tissue, the more your body will need to repair itself. The resulting cycle of damage and repair eventually makes muscles bigger and stronger as they adapt to progressively greater demands. Since our bodies have already adapted to most everyday activities, those generally don't produce enough stress to stimulate new muscle growth. So to build new muscle, a process called hypertrophy, our cells need to be exposed to higher workloads than they are used to. In fact, if you don't continuously expose your muscles to some resistance, they will shrink, a process known as muscular atrophy. In contrast, exposing the muscle to a high degree of tension, especially while the muscle is lengthening, also called an eccentric contraction, generates effective conditions for new growth. However, muscles rely on more than just activity to grow. Without proper nutrition, hormones, and rest, your body would never be able to repair damaged muscle fibers. Protein in our diet preserves muscle mass by providing the building blocks for new tissue in the form of amino acids. Adequate protein intake, along with naturally occurring hormones like insulin-like growth factor and testosterone, help shift the body into a state where tissue is repaired and grown. This vital repair process mainly occurs when we're resting, especially at night while sleeping. Gender and age affect this repair mechanism, which is why young men with more testosterone have a leg up in the muscle building game. Genetic factors also play a role in one's ability to grow muscle. Some people have more robust immune reactions to muscle damage and are better able to repair and replace damaged muscle fibers, increasing their muscle building potential. The body responds to the demands you place on it. If you tear your muscles up, eat right, rest, and repeat, you'll create the conditions to make your muscles as big and strong as possible. It is with muscles as it is with life. Meaningful growth requires challenge and stress.
Yay! Pork chop. Okay. There you go. So that's how it works. So why do people take steroids? Steroids are artificial androgens, and like testosterone. Testosterone's an androgen. They're superficial, and what they do is they will help you repair your muscles faster. And since you get a more rapid muscle repair, it usually takes a couple days for your muscles to repair themselves. But if you're on steroids, of course, you can repair your muscles, in a matter of hours. In which case, you could work out more. Now, if you took steroids and you didn't work out, it wouldn't build your muscles. It wouldn't do anything. I mean, the whole point of the steroids is to help you repair your muscles. So if you don't damage them, then you're never going to build muscle. So you have to work out with steroids. It's not like you can take steroids and all of a sudden muscles are popping out all over the place. It doesn't work that way. You have to work out. Okay. There are two reflexes that are maintained by the spinal cord that are automatic and are not mediated by the brain. The flexion reflex is activated when pain is applied to the leg. The muscles will contract, moving the affected area away from the stimulus. And we're going to watch one more video, I think. Oh.
The Hulk is an anthropomorphic exoskeleton which mimics the human form. It provides extra support that enables a person to carry more weight than they normally could. Exoskeleton technologies are considered part of the robotics field. If you want to think about them as wearable robots, that's pretty accurate. They sense what the user wants to do, where the user wants to go, and mimics the motion. We like to call these mantonomous systems. The exoskeleton is primarily composed of titanium components, which are both lightweight and provide the strength needed to carry the load. A microprocessor takes in readings from the sensors that are throughout the structure and calculates where the user wants to move, and then commands the actual hydraulic system to actuate the joints to provide the motion. You can walk, you can run, you can bend, you can crawl, you can leap. It does not impede your range of motion whatsoever. This technology could be a real benefit to the military. Just imagine you're a soldier operating at 6,000 feet in the Afghan mountains and being asked to take 120 pounds up in that level of thin air. How exhausted you would be once you got there. An exoskeleton provides the ability to carry that weight the same distance, but to have energy left to execute the mission once you're there. We've also looked at attachments that allow users to carry weight not only on their back, but also on the front. The exoskeleton will fit anybody between 5'4" and 6'2". The current system weighs 53 pounds, but it's pretty much unnoticeable to the user because what the technology does is it even transfers its own weight to the ground, in addition to the weight you're carrying. And we're taking the load off the soldier's back. And we're going to help prevent injuries that occur from carrying heavy loads and repetitive lifting tasks. The best part about working on this technology is that it gives us a glimpse into the art of the possible.
I can see them using that, and people that have those robots on will be called mules because they'll be carrying all the weight. But that's the future. In knee-jerk responses, the quadricep muscle is contracted to allow the knee to bend. Is informed of tendon pressure that makes the muscle react to stretching. Thus, the stretch reflex. And you've all been, if you've ever had a physical, they hit you right under the patella. They hit your patellar ligament, and it makes your knee, your foot kick. The primary lateral cortex, the M1, controls all the muscle movements in the body. The hands and the lips utilize the biggest portion of the area compared to the percentage of the body that they represent. The M1 communicates with the rest of the body through the pyramidal system. The pyramidal system is a triangular-shaped bundle of nerves that runs from the brain through the medulla and into the spinal cord. Lesions to this system will result in the inability to move select joints and limbs. Those neurons that run from the M1 to the muscles that are not in the pyramidal system are said to be in the extrapyramidal system. These neurons control the spinal reflexes. And we're going to look at the spinal reflexes right now.
Call your doorbell camera company and cancel the subscription. This brand new subscription-free mini...
Oh, perfect.
The lower body reflexes will be performed in the same manner as the muscle strength exams were performed. We're going to test one side and then quickly test the other side and compare side-to-side responses. We've got 5 reflexes that we're going to go over, one being the knee reflex, one the Achilles reflex, and then the adductor reflex, the internal and external hamstrings. The first one will be the knee reflex. I'm going to have the patient close their eyes, strike the tendon. We got a good response. I want you to keep your eyes closed. Strike it again. Got another good response. Now the Achilles reflex. I'm going to just slightly dorsiflex the foot by reaching underneath the foot and letting her rest the foot on my hand. And then I'm going to reach back and I'm going to tap the Achilles tendon. And I got a real nice plantar flexion of the foot. Comparing side to side. I have the patient lay face down. Now we can do the adductor, internal and external hamstring all in this position. If I'm going to test the adductor, I'm going to have the patient medially rotate the leg. I find the adductor tendon along the medial side of the leg. I've located it, and I'm going to strike over the tendon, and I get a slight contraction of the adductor. For the internal and external hamstring, I just have the patient lay flat. I locate the tendon by slightly having the patient bend their knee against resistance, bring the leg up. I'm going to push down. And the tendons pop out quite easily. I've got them, you can relax the leg. I've got the tendon located. the medial hamstring tendon. I'm going to strike the tendon, and I'm watching for contraction and slight flexion of the knee. On the lateral hamstring, I locate the tendon, and I'm going to do the same thing, strike the tendon, and watch for contraction of the hamstring as well as slight flexion of the knee.
And there you go, the spinal reflexes. Maybe. There we go. The extrapyramidal system communicates with the spinal cord through two tracts, the reticulospinal tract and the rubrospinal tract. The extrapyramidal system not only handles spinal reflexes, but muscles responsible for breathing and muscles that control the head and neck. And that is the end of that. So next week we'll tackle a couple more chapters. I'll see you next week.